All right, so in this video, we're going to take a look at two more examples dealing with integrals that are going to be evaluated using partial fraction decomposition. And so in this particular case, again, always start by thinking, is there an easy way to do this? If the answer is no, then we can investigate these alternate techniques. Being a fractional function, a rational function having a numerator and a denominator, we can go ahead now and hopefully get this thing to decompose okay. So what I'll go ahead and do is start with the 2x squared plus 3x plus 3 over the x plus 1, x plus 1, and x plus 1. Remember, for this to work, it's got to be factored completely, almost to the point where it seems a bit much. But I do have three different things now that I'm going to be needing to combine and add up to get my original result. We would have our x plus 1 here, and then we'd have our x plus 1 squared and our x plus 1 cubed. Okay, so remember, we have to take into consideration all possible ways to construct this common denominator, and this is the most exhaustive. All right, now they all came from linear factors, therefore we're still going to have the a, the b, and the c on top. Okay, so then I take this thing and I set it equal to, and I'll go ahead and combine now. This would be an a times x plus 1 squared plus b times x plus 1 plus c all over the x plus 1 cubed. So now I'm going to go ahead and take this numerator and set it equal to this guy. And while I do this, much like the last one, I'm going to go ahead and expand out this mess, and then we'll set it equal. So for this guy right here, that's going to give me now a ax squared plus 2ax plus a, and then the next term would just be the plus bx plus b. Then finally we would have the plus c at the very end, and that's going to be set equal to 2x squared plus 3x plus 3. Okay, so now to actually set up the system, I'll focus to start on my ax squared. Notice there's only one of those on the left, and we've got our 2x squared on the right, so therefore a must equal 2. In a similar way, if we focus on the x term, on the left we'll have a 2a plus b, and that's going to be set equal to the 3 that's on the right. And then finally, the a plus b plus c has to be equal to that 3. So a plus b plus c equal to the 3. There's your linear system that you can solve by substitution or elimination, whatever you prefer. Kind of jumping to the end here, a would end up equaling 2, b would equal -1, and c would equal 2 as well. So those are the numbers we take, we plug them in up here, and then we're ready to integrate. So these integrals then will be a 2 over an x plus 1 dx plus the integral of -1 over x plus 1 squared dx, and then plus the integral 2 over x plus 1 cubed dx. So three separate integrals. This is the only one that requires Calc 2 techniques. Both of these other ones are u subs. If you let u equal the inside on the bottom, then once you run through the process, it turns into a simply add 1 and divide type problem. So when all is said and done there, you end up with a 2 natural log absolute value x plus 1 plus 1 over x plus 1, and then minus 1 over x plus 1 squared plus c. So again, really nothing new in terms of the idea of partial fraction decomposition. I wanted to include an example here where we had this repeated factor so that we could remind you again on how this is going to be set up, and then of course getting the system set up as well. All right, so as we take a look at this next example, you can see in this one that denominator is just screaming at us to factor it, and it does have 4 terms, so we're going to factor it by grouping. So in that numerator, we're still going to have our 1. And in the denominator, from that first grouping, we're going to take out a 4x squared, which is going to leave us with a 4x minus 1. And Out of the second grouping, not a lot can be done, which is okay because we have that 4x minus 1 there we still need. So this thing is going to factor now into a 4x minus 1 times 4x squared plus 1 dx. Now moving forward with the decomposition process, since it's factored completely, and I've got these two factors, I'm going to have two things added together. I'll have my 4x minus 1 on the bottom here and a 4x squared plus 1 here. Now this comes from a linear factor, so we'll have our a on top, but this one comes from a quadratic factor. Therefore, we need to have a linear function on top of it. So that's going to be a bx plus c. Okay? So now, when we combine things, we'll have our a times 4x squared plus 1 plus the bx plus c times 4x minus 1 all over 4x minus 1 times 4x squared plus 1. And now, this numerator and this numerator need to be set equal to one another. So as I set those equal, I'll go ahead and simplify again like I have been. We'll have our 4ax squared plus a, and then for these other two, this is actually going to be a FOIL. So for my first, I'm going to get a 4bx squared, and then the outer would give us the plus 4cx. The inner would be a minus bx, and then the last would be minus c. And this thing here is set equal to 1. All right, so now if we look at our our x squared terms, that's going to tell us that we have 4a plus 4b equaling 0, since there are no x squareds over here. Similarly, we've got now the x terms, so a 4c minus b equals 0. And last, our constants. We'd have an a minus c equaling a 1. A minus c equals 1. So there's your system. And when you solve this now, you do end up with constants, a equaling 4/5, b equaling negative 4/5, and c equaling a negative 1/5. So I'm going to go ahead and move the screen up a little bit here to hopefully not cut off everything, but just give me enough room. So when I look at this now, the actual numbers being plugged in up here are going to leave us with the two integrals of 4/5 over 4x minus 1 dx, and then plus the integral. Since our b is negative 4/5, we'll have a negative 4/5 x minus the 1/5 over 4x squared plus 1 dx. So again, just plugging in the numbers is going to give us a little bit of a messier numerator over here. But then to actually expand this out and compute this integral, I would take this denominator and I would go up separately into both of the terms from the numerator and create two integrals from this one. At the same time, I will go ahead and pull the constants out as well. They're just kind of in the way. So there's our first one. Then we'll have a minus 4/5 integral x over 4x squared plus 1 dx, and then a minus 1/5 integral 1 over 4x squared plus 1 dx. And again, all I did going from here to here was take this denominator, split it up into that one for this integral, and up into that one for this integral here. Okay? So this one and this one as well will actually end up being Calc 2 integrals, both of which you could do using a U-sub. We've done these many times before. This first one is going to turn into a 1/5 natural log absolute value 4x minus 1. And for this other one, I definitely would recommend writing out the U-sub, because as you write it out, it is going to take into account the x on top, but it still will turn into a natural log once we actually integrate. So I would encourage you to actually write out that U-sub there to see that we would in fact come up with this negative 1/10. Natural log absolute value 4x squared plus 1. And then for the last integral, this one's from the last chapter. This is an inverse tan integral. It's not too difficult, but again, I would encourage you, if you need to write it out, feel free to write it out. But it does give us a negative 1/10 inverse tan of 2x followed by that plus c. All right. So the whole idea is, again, mostly algebraic in nature. All of this blue stuff here is nothing but algebra. What we're doing is we're taking something that's not very easy to integrate, we're making it into multiple things that are simpler and then easier to integrate. And hopefully you've seen that in the last few examples. Don't forget previous techniques. We saw an inverse trig function came out of here. You certainly can have trig subs. You can have other types of applications that you might run into as well. So just be on the lookout as you work through this process.